Hello, everyone. Good day. Today, I would like us to take a topic titled Kirchhoff's Laws. This lecture will be presented to level 4 students taking electrical technology. I've also made some assumptions, one of which is that students taking this module do not need to have any prior knowledge of the subject. Now, before we can proceed, I would like to highlight the learning outcomes. At the end of this session, students are expected to be able to state Kirchhoff's law, starting with the Kirchhoff's current law, and then apply the Kirchhoff's current law in solving basic DC problems. They should also be able to state Kirchhoff's voltage law and apply the KVL in solving DC problems. Now, let's start with the first law, the KCL, the Kirchhoff's current law. This law states that at any junction in an electrical circuit, the total current flowing towards the junction must be equal to the total current flowing away from the junction. What do I mean by that? So if you look at this circuit, this is a sub circuit. This circuit, you see, there's a node which we normally refer to as junction in electrical circuit. And at this junction, you can see that the current I1 and the current I2 are both flowing towards the junction, towards the node. While currents I3, I4, and I5 are flowing away from the junction. So what this law tells us is that at this junction, current flowing in, which are currents I1 and current I2, must be equal to current flowing away from the junction, which are current I3, current I4, and current I5. So if that is true, it means that I1 plus I2 must be equal to the sum of I3, I4, I5, which leads us to this equation. You can see here that we've said that I1 plus I2 is equal to I3 plus I4 plus I5. If we transpose, we now get that I1 plus I2 minus I3 minus I4 minus I5 must be equal to 0. So this is the first law of Kirchhoff. It's a very basic law. All current flowing towards the node or junction must be equal to the current flowing away from the junction. Now let's apply this law in a given problem and see how that pans out. So let's look at this problem. This example says, which of the following statement is true for the junction in the network shown below? So this is a junction. You can see here that looking at the arrows, you can see that I1 is flowing in, I5 is flowing in. However, I2, I3, and I4 are all flowing away from the junction. So if that is true, we need to look at the options A, B, C, and D and determine which equation satisfies this condition. I mean, if we apply KCL. So let's take it one at a time. Look at the first equation A. You can see here that from equation A, I1 and I5 are not on the same side of the equation. So there's an equality sign. You can see that I5 is on the left-hand side, while I1 is on the right-hand side. That simply tells us that that equation is not correct because I1 and I5 should be on the same side of the equation if they retain positive signs. Let's look at equation B. Here we see that I1 is on the left-hand side, I5 is on the right-hand side of the equation. Again, they are both positive. That is not true because I1 and I5 should be on the same side of the equation if they are both positive. Let's look at C. Again, we have I1 and I5 on different sides of the equation. Therefore, this is also not correct. Now, let's look at D. Here we have I1 plus I5 on the same side of the equation. And then we have I2, I3, and I4 all negative on the same side. Meaning I2, I3, I4, if you take it to the other side of the equation, if you transpose, it will all be positive. Therefore, we can conclude that equation D is the correct answer. Let's check. So equation D is correct. Moving on to the second law. Now, this law has to do with a loop. Don't forget, the first law happens at a node or a junction. The Kirchhoff's voltage law, which is the second law, happens in a loop. This law states that in any closed loop in a network, the algebraic sum of voltages or voltage drops taken around the loop must be equal to the algebraic sum or the EMF acting in the loop. What does that mean? Let me simplify that. Here we have an EMF, electromotive force E1 and E2. Electromotive force E1, electromotive force E2, which is what we call the EMF. So what we are saying here is, if you take the voltage drop across all the given resistors like R1, R2, R3, they must be equal to the algebraic sum of E1 and E2. Right? Now, before we can solve that problem, you need to note that current flowing away from the positive terminal. Now, in a cell, the longer arm is the positive terminal. So current flowing away from from the longer arm is considered to be positive, right? So if that is true, it means that in this circuit, E1 is positive, while E2 is negative. Why is E2 negative? Look at E2, you can see that the current is flowing towards the positive terminal. So it will be negative. But if it's flowing away from the terminal, then it's positive. If that is true, then we can say that E1 minus E2, because E1 is negative, positive, and E2 is negative, is equal to the algebraic sum of the drops across each of the given resistors. Again, let's try this in an example. Here we have a loop. If you look at this loop, we have three EMFs, E1, E2, and E3. We also have three resistors, R1, R2, and R3. So what we need to do here is to apply the same technique and see which of these results are correct. Now, you can see here that we have the direction of flow of current is counterclockwise. If that is true, it means that E1 should be positive because it's flowing away from the positive terminal. E3, E3 here should be negative. Why? Of course, E2 also should be negative. So anytime current is flowing away from the positive terminal, it's positive. So if we take all of that, we can now see that the first equation here does not satisfy the KVL because E1, E2, E3 are all positive. That shouldn't be, right? Now, don't forget we said only E1 should be positive. So if you look at this one here, you can see that E2, E3 are positive, E1 is negative. Now, this could be true because it is possible that E1 has moved across the equation sign, the equality sign, right? However, if E1 is negative, then this equation, this component shouldn't be negative as well. So that tells us that B is incorrect. Now look at C. If you look at C, you see that E1 is positive, E2 and E3 are all negative. That's, again, if you think about it this way, you realize that E1 is positive, which is what we expect. E2 is negative, and E3 is negative. So that means C should be the correct answer, right? So if you check here, I said that the correct answer is C. Now, for lack of time, I would have loved to go through this with you, but what I want you guys to do is try to work in pairs and solve this problem. Again, this you can see that the law to apply here is the first law because there are nodes. You can see there's a junction there. To apply the first law to determine all the given current I1, I2, I3, I4, and I5. But if you look at this, you realize that you cannot start from just any node. You need to find a junction where there are two knowns and one unknown. So look at this junction here. The only unknown there is I2, so we can actually start from that junction. So from that junction, you can see that 10 amps plus 50 amps means that I2 is 60 amps. So that's how we arrive at I2 is 10 amps plus 50 amps, which is 60 amps, right? So if you go through all of it, you'll be able to verify all of this. If you don't get anyone correct, please let me know and I'll be happy to come back and explain this. Again, we have another equation here in a loop. Again, here we have EMFs, which is 4 volts, 3 volts, 6 volts, and E. We are asked to find the EMF E, which is the unknown. So if you apply KVL in that loop, you will arrive at 9 volts. Please go through this in your groups, in pairs, and let me know if you need any clarification, right? Finally, I hope you've learned something from this class. What I expect you guys to do is to work in pairs and solve the worksheet I've provided. I'll be here. If there's any question on how to navigate any challenge or challenges, please do let me know. Thank you as I look forward to getting the feedback from your solutions. Bye for now.